Hello friends, welcome to the course Essentials of Data Science with R Software 1, in which we are trying to understand the basic concepts of probability theory and statistical inference. So now you can recall that in the last two lectures we had discussed the bivariate probability distributions when we have discrete random variables. And in the last lecture we discussed the implementation in the R software. Now, in this lecture, I am simply going to extend the concept that we have learned for the case of discrete random variables to a continuous random variable, right. And as I discussed towards the end of the last lecture, that how are you going to handle the data on such variables in real life, that we already had covered. So, I need not to show you once again that how are you going to do such an analysis in the R software. So, my objective in this lecture is merely to give you the expressions of the same quantities that we had understood in the earlier lecture, like as probability mass function, marginal probability, conditional probability functions. Now, I will try to define them in a different setup when my random variables are continuous. So, we will have the concept of joint probability density function, marginal probability density function, conditional probability density functions, and so on. And you know one rule, that whenever we are trying to deal with the discrete random variable, we are trying to obtain different probabilities by summation over x or summation over y or summation over x and y, etc. But when we are trying to deal with the continuous random variable, we simply have to replace them by integral sign, but appropriately. Yeah, you cannot close your eyes and just replace it. You have to do it following the mathematical rules. So, let us begin our lecture, and I will try to give you all the definitions and concept that we have discussed in the case of discrete random variable, now for a continuous random variable. Okay. So, suppose we have here two random variables, capital X and capital Y, which are now both continuous. So, the joint probability distribution of X and Y can be specified by providing a method for calculating the probability that X and Y assumes a value in any region R of two-dimensional space. Well, do not get confused with this R, that is the R software. This is the space of real numbers, right. So, if you try to see, we already have defined the concept of probability density function, where we have given this interpretation that if you want to compute the probability of an event, then it is going to be an integration over the range of the variable in which the event is going to occur. So, similarly, the concept of probability density function of a single continuous random variable can be extended to a joint probability density function and can be defined over a two-dimensional space or a multivariate dimensional space. So, now first we try to define the cumulative distribution function, but in the case of joint probability. So, we have the definition of joint CDF, right. So, a bivariate random variable x y is continuous if there is a function f x y such that you have to keep in mind that we have the that we had earlier denoted by small f the PDF and by capital F the CDF, right. So, the same symbol will continue here also. So, this joint probability density function is such that capital F x y, that is the CDF or the joint CDF of x and y at the values small x and small y, which is actually the probability that x is less than equal to x and y is less than equal to y. So, this can be obtained by the double integral minus infinity to y and minus infinity to x and the joint PDF f x y dx dy wholes, right. So, this f x y, this is the joint CDF of x and y, and if you try to see, we have just extended the definition of a univariate CDF to a multivariate CDF. The only thing will be that instead of here having a univariate integral, you are going to have here bivariate integral and double integral, and in case if you are going to deal with more than 2 variables, you simply have to solve a multiple integral, that is all. The main thing is this, what are going to be the limits, that is the most important part whenever you are trying to deal with multiple integrals. Okay. Now, you can recall that we had given couple of conditions for a CDF, and similarly we have here condition for the joint CDF of x and y. They are as follows, that limit x tending to minus infinity f x y, x y should be equal to 0, limit y tending to minus infinity f x y should be equal to 0, limit x tending to plus infinity, limit y tending to infinity f x y should be equal to 1. Right, and if you try to see, these are the simple extension of the same definition that you use in the case of univariate. Right. There is one more condition here, that f of x2 y2 minus f of x1 y2 minus f of x2 y1 plus f of x1 y1 should be greater than or equal to 0 for all x1 s2 y1 y2 such that x1 is smaller than x2 and y1 is smaller than y2, and this is called here as a rectangle inequality. Actually, this is like this, that here there is an x1 x2 and there is an here y1 and here y2. So, this is the area, and this inequality is simply trying to ensure that the this quantity here that is going to indicate this area, and obviously this area has to be always greater than or equal to 0. The area cannot be negative. So, this is what it is trying to ensure. Right. Now, let me try to take here one example and try to explain you how are you going to compute it. Right. So, that will give you some idea. So, suppose the joint PDF of x and y is given by this quantity f x y, and which is e raised to the power of minus x plus y when x is lying between 0 and infinity, y is lying between 0 and infinity, and 0 elsewhere. So, if you want to find out here the joint CDF, that will be the integral minus infinity to x minus infinity to y and exponential of minus t1 plus t2. So, this t1 is corresponding to x and t2 is corresponding to y. So, this will become here dt1 dt2, and if you simply try to solve this integral, well, I am not going to show you here, but I believe that you can solve such integral without any problem. This will come out to be 1 minus exponential of minus x into 1 minus exponential of minus y for x and y being lying in the interval 0 to infinity and 0 otherwise. So, you can see here this is how the joint CDF will look like. Right. Now, we come to the aspect of marginal probability distributions. Right. Now, I do not think that if there is any need to explain what are the marginal probability distribution, because we already have understood them. So, now whatever the approach you adopted in the case of discrete random variable in defining the marginal probability distribution, a similar approach is going to be adopted in the case of joint PDF also. So, right. So, if we assume that our joint PDF is f x y, then we simply have to define the marginal distribution of x and marginal distribution of y, and you will see that we are simply going to replace the sum by integration. But yeah, you have to do it following the rules of mathematics. Right. So, the first question comes here, that what is the joint PDF? First, we try to define or give a formal definition of the joint PDF, and then we will come on the marginal PDF. So, do you remember that when we defined the probability density function in the case of univariate continuous random variable, the same definition is going to be extended over here also. So, suppose if I say that there are two continuous random variable f x y and their joint probability density function is going to be denoted by f x y x y. So, small f is going to indicate the probability density function. So, we assume that f x y is greater than or equal to 0 for all choices of x and y, and minus infinity to plus infinity, minus infinity to plus infinity f x y dx dy should be equal to 1. That means earlier you had assumed that the total area under the probability curve is going to be 1. Now, the case is going to be in 2 dimension, right. And then for any region A, in a two-dimensional space of a real number, the probability that x y belongs to some region A. This is going to be the integration over the range of the region of A, and then f x y dx dy. Right. So, this typically this f x y is defined over all of two-dimensional space by assuming that f x y is equal to 0 for all point for which f x y is not specified. That is the same definition that you did in the case of univariate. Also you define the probability. For example, if you try to recall the uniform distribution, you define the probability space only between the 2 points A and B, and beside those points the value of PDF was 0, right. So, for example, if you want to compute here the joint probability that x is lying between x1 and x2 and y is lying between y1 and y2, then this can be obtained by the double integral y1 to y2, x1 to x2, fxy dx dy, right, exactly in the same way as you did in the case of univariate CDF, that you used to integrate the probability density function over the values of the random variable. Right. So, now about the marginal probability distribution. So, that we have already understood that if more than one random variables are associated with the random experiment, we distinguish between the joint PDF and the PDF of each variable individually. Right. So, this individual probability distribution of a random variable is referred to as marginal probability distribution. Right. So, this marginal probability distribution function of x can be determined by the joint probability distribution function of x and other variables, in case if you are trying to deal with more than two random variables. Right. For example, in case if you are trying to deal with three random variables, you have a trivariate probability density function, then you have to remove two variables if you want to find out the effect of one variable. For example, if you want to find out the marginal of x, then you have to remove the effect of y and z. So, now we try to formally give you the basic definition of marginal probability distribution. So, in case if you can recall the definition or the way we had introduced or understood the marginal probability mass functions in the case of discrete random variable, the same concept is going to be here. For example, if you have a probability joint probability functions like I said pxy, and if you want to find out here only the say here px, what you were trying to do? You were trying to sum over the y. Now, I will say simply you have to replace this summation by integration, and that is obvious. You are you have a joint effect, and you want to find out the effect of one variable, you have to remove the effect of another variable. So, thinking in this direction, the marginal distribution of x can be defined as f of x, which is equal to integral over the joint PDF fxy, but the integration is to be done over the range of y. So, this is the range of y, and then you are integrating it here with respect to y. So, obviously, the effect of y is being integrated out. So, so now whatever is left, that is the effect of x, and this is how you can remember that whether you want to integrate with respect to x or with respect to y, because many times students get confused, right. So, in this case the integral is over all the points in the range of y, and similarly if you want to define the marginal distribution of y, then it is defined as the same quantity, the integral over the joint PDF, but now the integration is with respect to x. And now if you want to ask me that how are you going to extend it, so I will say here simply here, suppose you have a probability density function of say here three variables, say f of x, y, z, and suppose you want to find out here only f of x, then this is going to be integrated over the value of y and z dy dz, right. So, that is pretty simple. So, you can see here, once you understand the bivariate, extending it to trivariate or any order or say multivariate setup is not difficult for you, right. And definitely that means you have to take care of the range of y, right. Okay, so now I give you one more concept. Once you can define here the marginal distributions of x and y, why can't we define the cumulative marginal distributions of x and y? That means this marginal distribution is also going to be just like another probability density function, which is looking like a univariate probability density function, and you earlier defined the CDF for a univariate probability density function. So now I can define the CDF exactly on this univariate probability density function, which we have called as marginal distribution. So now it is very simple. You simply try to take here the marginal distribution here f x, and we try to define the cumulative marginal distribution of x indicated by f of x, and this is here the same thing, means minus infinity to x integral f x t dt, and this is the same as limit y tending to infinity f of x y x y, right. And similarly, you can define the cumulative marginal distribution of y as f of y y, where the integration is going to be over the range of minus infinity to y over this marginal PDF of y with respect to t, and this is the same as limit x tending to infinity t x y, and so this is the joint CDF f. Right. So, you can see here that it is not difficult. You are simply trying to look this marginal distributions of x and y as in two individual probability density functions. So, whatever you have learnt in the case of probability density function, all those results, theorems, concepts can be extended here. Right. So, now we try to consider the conditional probability distribution. As you have means found the marginal, so similarly we can find out the conditional distribution also. So, suppose if there are two continuous random variable x and y, so I can define the conditional distribution of x given y and y given x, and what is their interpretation, how they are going to be used, that we already have discussed many times, right. So, I will say here, if you want to define here the conditional distribution of x given y, so this will be f of x given y, and definitely this is going to be now here a function of x, that you have to remember, because out of these two values x and y, now y is known. So, this is no more stochastic. So, this function is going to be here function of only of x. This is what you have to understand in this case. So, this is going to be defined here as say joint PDF divided by the marginal PDF of y, and yeah, means obviously this is f y y has to be greater than 0, means otherwise this quantity cannot be defined. And similarly, the conditional distribution of y given x can be defined as say f of y given x, and this is going to be now function of here y, because x is fixed, x is known. So, this is going to be joint PDF of f x y divided by marginal PDF, right. So, and yeah, obviously in this case f of x has to be greater than 0. Now, if I ask you, how will you find out the conditional distribution? It is very simple. You will have the value of joint PDF, you can obtain the value of the marginal PDFs, and then take the ratio, means after following the rules of mathematics, and then you try to find out that function, that is all. And now, once you can define here this conditional PDF, do not you think that this is just like a probability density function. So, this should also satisfy the rules on the same lines as of PDF, right. So, this conditional probability density function will satisfy these three properties exactly on the same way as you did in the case of simple univariate PDF, that f of x given y x should be greater than or equal to 0, integral over y f of x given y dy should be equal to 1, and the probability that x belongs to a given y equal to y for any set a in the range of x, this can be obtained by here the integral over the range of x for the set a into the conditional PDF f of x given y dx. So, this is what we have defined for the conditional probability of x given y, and similarly you can define for the f of y given x, that is the conditional probability density function of y given x, right. And this and if you want to define it for the discrete random variable. Exactly, you can define in the same way, right. Now, once you have defined the joint random variable, don't you think that we should also define the expectation? Yes. So, now we are going to consider the expectation in the case of bivariate probability density function, right. So, suppose gxy is a function of random variables x and y. So, the conditional expectation of gxy for given y equal to y is that expected value of gxy y given y, it is equal to integral minus infinity to infinity gxy f of x given y is equal to y dx. Now, here comes sometimes a confusion among the minds of a student whether they have to take it here the range of x or y. For example, here we have taken here the range of x. So, if you try to see here, there is a very simple logic by which you can understand this variable gxy given y equal to y. What do you think? This is a function of x or a function of y? Y is actually here fixed. So, this is only a function of x. So, when x is a random variable, you know the basic rule that if you want to find out an expectation, the expectation of x is integration say fx dx. So, you have to choose this variable here appropriately. Right. So, because I can write down here that this is an integration over the range of x. And similarly, if you want to find out the conditional expectation of gxy for given x equal to x, you simply have to use the same definition, but you have to now integrate it with respect to the range of y. This is what you have to keep in mind. So, you are simply trying to treat this conditional PDF, marginal PDF just like a simple probability density function, and the way you have found different types of things, they can be obtained here also, right. Now, I try to give you here some results which are very particular results related to the such conditional distribution, right. So, in case if you try to define here the expectation of gxy given x equal to x that we have just considered, we have now understood that this is going to be a function of here x, phi x. One thing, do not get confused that this is the CDF of normal distribution, this is some function. So, this is not the CDF of normal 0 1, remember one thing. Right. Okay. So, now the result here is that if you try to find out the expected value of phi x, this is going to be the same as the simple expectation of gxy. And how to find out the simple expectation of gxy? That is going to be simply here integration over the range of x and y gxy into f of xy and dx dy. That is all. Right. So, you can see here what is really happening. You are trying to take the expectation of a conditional expectation. Phi x is his conditional expectation. And now, you are trying to take this here expectation E operator here. This E is unconditional expectation. Right. So, you are trying to take an unconditional expectation of a conditional expectation, and this is coming out to be same as the unconditional expectation. Right. That is a very important result. And this is also indicated here like this, what I have shown you here, that this is expected value with respect to the random variable x, and this is the expectation with respect to the conditional random variable x given y equal to y, and this is here exy, this is the expectation with respect to x and y, that is the joint PDF, right. So, now if you try to see, I am trying to see here that first you try to take the conditional expectation, and then if you try to take once again the unconditional expectation of the conditional expectation, this is going to be same as the unconditional expectation of gxy. This is what I want to say here, right. So, now in case if you try to take here gxy equal to y, then expected value of y is simply going to be expected value of a conditional expectation of y given x And in case if you try to take gxy is equal to x, then expected value of x is going to be the unconditional expectation of a conditional expectation of x given y. Right. So, now based on that, if you want to find out the variance of such a variable, then the conditional variance of x is obtained here in a different way. Right. For example, in case if you try to simply want to find out the variance of say x in the case of the conditional distribution of x given y, then it is defined just exactly in the same way as you have done in the case of univariate. For example, if you try to take here conditional variance of x given y equal to y, this is you just try to take it as a new random variable here z, which is the conditional random variable, and simply try to define here expected value of x square minus expected value of x whole square. So, this will become something like based on the condition of y given y. So, you can write down here this something like here z is expected value of z square minus expected value of z whole square. So, this will simply be the expected value of x square, which is obtained from the conditional expectation or the conditional distribution of x given y. This is the expectation of x given y, and by solving this you can simply compute the variance. But now, what I want to show you here is the following, that the variance of x in this joint distribution, this is obtained as variance of expected value of x given y plus expected value of variance of x given y. This is a very important result, and it is very different from the univariate case. Right. So, variance of x is obtained as has here variance of conditional expectation plus expectation of conditional variance. Right. So, this is something like variance of conditional expectation plus expectation of conditional variance. Right. So, this is what you have to use when you try to solve any problem. Right. Now, I come to the last topic of this lecture, where I would try to give you some idea about the stochastic independence. We already have discussed this concept while dealing the concepts in the probability theory, that how do you define the events to be independent. At that time we said if there are two events A and B, then we say that if the probability of A intersection B can be expressed as probability of A into probability of B, then the two events are independent. And we also had discussed the interpretation of this concept, that the occurrence of one event is not going to affect the occurrence of other event. Now, the same thing can be defined here, that the two continuous random variable x and y are said to be stochastically independent if f of x y is equal to f of x into f of y. Right. That means the joint probability density function can be expressed as the product of their marginal density function. So, this is here joint PDF, and these two are the marginal PDFs. If you can satisfy this condition for a given joint PDF, then the random variable x and y are going to be independent. Now, at the same time, I would also like to extend this definition for a discrete random variable case also, that if x and y are two discrete random variable, then if their joint probability, that probability x equal to xi and y equal to yj, can be expressed as their marginal probability, like probability of x equal to xi into probability of y equal to yj, and if this is valid for all values of I and j, then we say that the two discrete random variables x and y are independent, or they are stochastically independent of each other. And the same definition can be extended or can be written using the concept of CDF also. So, in terms of CDF, if we have a joint CDF of two random variables x and y, like as here capital f x y, we say that x and y are stochastically independent if the joint CDF can also be expressed as the product of their marginal CDF. So, on the left hand side we have here a joint CDF, and on the right hand side we have here the marginal CDF of x and y. So, So now you can see that here I have given the definition of this stochastic independence using the PDF as well as CDF. Right. So, similar definition can also be given in terms of the expectation of the random variables. Right. So, two random variables x and y are said to be stochastically independent if the expected value of x y is equal to expected value of x into expected value of y. Right. So, what you have to do? You have to just find out the joint expectation, and then you have to find out the expectations which are obtained from the marginal distributions. Remember one thing, this is obtained from the marginal distribution, and this is obtained from the joint distribution. Right. So, from the joint distribution first you have to obtain the marginal distribution, and then you have to take the expectation that will give you these values. Okay, so, if you can satisfy this condition, then the random variables are going to be independent or stochastically independent. So, all this definition whatever you have given here in terms of PDF, CDF, expectation, etc., they can be extended for any finite number of random variable. For example, if I say here, if I have random variables, suppose here x1, x2, suppose here xp, and we want to check their stochastic independence. So, in terms of the PDF, you will have here f of x1, x2, xp, x1 of x2, xp. This can be written as the product of I goes from 1 to p, f of xi into xi. That means the probability that the marginal probabilities are obtained for each of the variable and then their product. And then if you want to write in terms of here joint CDF like this, then this has to be written as the product of their marginal CDFs, right, f of xi, see here xi. And similarly, if you want to write down it in terms of expectation, then expected value of x1, x2, xp, this can be written as a product of I goes from 1 to p, expected value of xi. Right. So, this is all about the stochastic independence. So, now okay, if we come to an end to this lecture, and you can see here that this lecture was only theoretical, and but my idea was only to extend the definition whatever you have learned in the case of discrete distributions. So, this is what I have done in the case of continuous distribution. So, after this, yes, as expected, I will try to take some examples and will try to show you, but the reason why I am stopping here is that I have introduced here a couple of concepts. In the next lecture, I am going to take some examples and I will try to show you that how these values are computed. So, but it is very important for you that before you understand those applications, you have to understand their fundamentals. So, I would request you that you please try to revise this lecture, try to understand the definition of all these quantities, and in the next lecture, I will try to take some example and I will try to implement them. So, try to revise and practice, and I will see you in the next lecture. Till then, goodbye.